blocked, so I'm just gonna ignore it. So first thing I'm gonna talk about is if we have this is not going well, is it? Hmm. To identify an equation, so that's what we're gonna talk about. For example, we could talk about this equation in its fullest length. So we have this equation, and in mathematics, we think of it as inputting values into this and getting an output. But if we, in the real world situation, we would need to know the input and output and how we compute it to figure it out. And I guess I could talk about politics too later on, because if you think about politics, we don't really know the output, the system basically, with the parameters inside of the system parameters. Oh my god, writing it down is such a bore. We have inputs, and we have two ways. I mean, we usually have one way to go, which is outputs that are unexpected. Um, expected, and usually doesn't get expected. What I'm talking about is like policies and other stuff like that. Usually, when we talk about policies, it is inputted in, like, for example, we want to build more houses, but who's going to pay for it is one question, and the outcome if it's higher taxes, probably. But higher taxes does not lead to bigger income, so this is a reciprocal situation because we expect more income if we increase taxes, but usually workers don't want to work as hard because most of the taxes is going to be stolen by the government. And then we have a down trickle effect of the economy, then the schooling system. It's kind of the output is unexpected, and the saying that we know what will happen will lead to something unexpected happen. So you do not want to trust policies. For that example, equations in physics are the same. We expect that if we have an input and output, we will get something out of it that's correct and well defined. But if you do an experiment, you know there's errors in each of these. There's definite errors on each of this. And not only errors, a completely wrong answer you can get. Completely wrong. The measurements you might have did almost perfectly, but it's just because of the electrons not flowing correctly, or there's a little sidebar here that has metal over here that transfers some of the electrons, or even not electrons. The wire might have had some resistivity in it, and you can't really fault the measurement because that's the entire ecosystem of a lab. Errors on errors on errors. We try to minimize it, but it's not always practical or logical. It will happen like that. So yeah, that's one of the major continuities of equations, and the first thing we should always talk about when we talk about equations. Next thing I want to talk about is probably not vectors yet. I do want to talk about vectors, but the meaning of the equation. So A, we would assume that's surface area, and this would be the length. And to a certain degree, you are correct. The problem is for a certain idealized situation, it's better to not say it's area, instead it's just length. What kind of situation could possibly lead to this situation? A light bulb. That's very horrible drawing. I don't like that drawing. Huh. Alright, let me do a little bit more cartoonish style. Yeah, that's better. Yeah, you see that? That's good. Okay, that's better. So let's just say we have some electrons. The arrows indicates where the electron goes to. But if you span the wire out, you would realize that it is basically one big so this portion over here, you would expand it to this length, and you realize that it is electrons going into the system. One thing a lot of people don't realize is when we talk about this, we actually, if we define the equation of this, you would find that this is the definition of it. Um, Usually, the definition that's given for the resistivity, this is actually resistor, the resistivity, or are known as resistivity, um, uh, defined by this unit over here, the SI unit that we care about. Unit means standard units that scientists uses quite often. So this is usually the surface area over here. This area, the surface area is considered surface area. And then usually the length over here is called L. And if we talk about L, then this is area. But in this case, the area is like a dot over here. It's like a dot. And then it goes like this. In this case, we can think of it as a line. We're no longer thinking in terms of 2D and we're thinking of 1D. What does that mean? Well, this basically means there's no resistivity. But um, for let's just say in this case, it was we have something like this. So and then we have some notable interest over here. Let's just say that the area equals 0.05, and then the length over here is 10 and something like that. You can obviously see that's just going to be a big, insanely big number as the resistivity R with the P. P is density, which is defined by the material. Um, so we can simplify it to a 1D system usually. And that's the whole idea of what I'm trying to say, is or 2D system. It depends on what the situation is. So if we have, if you're drawing this length over here, you could say that the area over here is 2 meters, and this is 5 meters. That 2 meters just a line, and will not be defining anything else, and we'll be using that as our area basically. Uh, 2 times 0 is nothing, so you have to define it by that logic. It doesn't always work out like that, but that's what I'm trying to imply here. Okay. In reality, to me, alright, I'll explain it better somewhere else actually. But yeah, so I was trying to get to the question making. So let's actually go to oh yeah. So scalar and vectors. In the real world, we have more vectors are more useful to us than scalars to us. And you might think there's no vectors, but in reality, we have a lot of tiny vectors. If you throw something up in the air, I don't know, with different velocities, or let's just make this bigger so we can actually think of it as throwing it like this, with the center of mass. And the V over here, we have tiny velocities that keep on changing over here. And that's what we call vectors. You know what? This is I'm just testing this out to see if, you know, the thing is, you have to keep on testing yourself because usually if you don't do this, you won't get any better. So let's just keep on going. Because I don't want to look like a fool when I actually try to teach other people about the content I know in my brain later on. So we're going to keep on fooling myself on the internet, and that'll be fine. So vectors have a direction and magnitude, but the direction is one way. That's the worst way to describe it. Hmm. Yeah, I don't know if that's the right way to describe it. I mean, we could just bring up the questions I made, and this is the questions I make myself, but um, it really does not teach you the method. It kind of teaches you, but won't really help you at all. And I'm pretty sure this is wrong. I don't know what this is actually. I forgot what that is. Funny enough. So yeah. So how do I describe this without getting fucked up? because a lot of people will get confused when we talk about the wheels and how the angle of the space displacement does not work in a similar light to displacement. And displacement is a vector, and then radians and angular velocities and all these must be vectors, right? Which we'll get into, but that's confusing in a way. Why does that work that way? So, uh, especially in a theoretical situation of speed and velocity. All right, if I said that this atom moves at the speed of 5 meters per second per sec, um, just outwards, you wouldn't know what direction it is going at, where it's going, to be precise. If this actually works, yeah. If I was to give a direction like northeast, or I guess this is this way, west this way, uh, this I guess this works actually perfect. So if you move this way, we're showing a direction, and we don't have this mystery question we have over here. We have a question of 5 meters per second, but do you mean 5 meters per second everywhere? And that would imply a ripple. I guess you could do fluid, and then it would be like all direction, like a bunch of atoms going. I don't actually know that, but that's a good question. What would physicists call that? Fluid dynamics, but would that be considered I guess each individual particle would be considered a vector, but if it was something like this 5 years ago, you have to assume that it's just going somewhere, and it could be just magic at that point. Um, so sorry about that. My phone just had something turned on. All right. So yeah, I guess explosion could also work as something moving at 10 meters per second, but in all directions, like the air particles. You could definitely say that, but there's individual. If you were talking about individual air particles, you would have to talk about that as a vector. If I were to draw a ball and then it goes somewhere, it obviously has a vector. You're not going to say that this ball moves 5 meters per second and have it have no direction on where it moves, because that would be impossible. A ball would have to have a direction when it's going 5 meters per second, right? Wrong. All right. How about if you don't have a standing point? If you're going at the same speed as the ball, you wouldn't see it as moving, and that's, I believe, the first law that Newton created, Newton's first law, which actually that's a good way to translate to first law. We can talk about this, and then we'll talk about Newton's first law. That's a good motion, movement. Yeah, that would work. Yeah, that would work. And then we could talk about integrals and their definition with constants too, because we may be learning this in calculus, this topic about integrals in calculus, but you don't know what that means until you get into a lot of physics, reality. Because what is that C? That C, you have really a cloudy judgment. You don't really know what that means. You know it's a number, but yeah, and that's it. That could also be a transition point you can talk about. Okay, that's an interesting idea. Yeah, but I can see myself translating from this talk to first law explosion. Yeah, that would probably be the best idea you could think of. But then, hmm, you're assuming you already know 20A shit, which is calculus 20, calculus. Huh. How would you explain calculus to a kid? Well, it's basically limits at that point, and you would need to talk about how minuscule and small the difference are in each and every change of it. Huh. Yeah, we're gonna have to put a pin on that actually. But yeah, this is a basic idea of Newton and then velocities and speed. But we don't really talk about kinetics at this point. Yeah. Without calculus, the next step, I'll have to jump and not talk more about Newton's law. And we'll have to jump on here because if we talk more about Newton's law, it wouldn't make any freaking sense. So what I would have to do at this point is say that Newton's law is on hold, but just introduce it. That's probably the best avenue at this point, which is and then what would I talk about? Next topic I would talk about is basically kinetics and the ball being jumped, because we got the idea of a velocity, and we can do questions if we wanted to, but that wouldn't really help anyone. And then we would have to talk about second law in terms of Newton's kinetic equations. Otherwise, it wouldn't really make sense, which is F equal ma or A equal F divided by m. Force is another topic, but that causes another acceleration. Now, for now, to simplify, the easiest way to say something here is to talk about gravity and its constant A acceleration. And doing it like this would be confusing. I wouldn't recommend it doing it this way. The way I'm drawing with the blue arrow, I should not be doing that. I should really say that out loud. Blue arrow, that way you shouldn't do it, because it confuses it with velocity. Because we are gonna we're gonna you when you do this, most of the time we talk about a velocity vector, and that squiggly symbol means vector, which means it can change with time. So I guess the easiest way to say it is like this method over here. But you also need to define the positive direction like this. Usually people don't care, but some people really care. Depends on the teacher. I don't care, but a lot of my professors didn't care. Just a weird guy, so I don't that care a lot. Um, this equals 9.8 meters per second square, but usually you just want to leave it 10 meters per second square. Why? Because usually measurements to the third is not really that credible for certain situations. So 10 meters per second square is perfectly fine. Now we need to talk about calculus to understand what I'm actually talking about. I hate going to algebra because it doesn't really help the understanding of how we got the equation. You could always assume that you got the equation by doing a lot of shit, but that's not critical thinking. Alright. Actually, maybe it's better to get to my calculus notes. Yeah, that's the idea of a dream. Huh, it's a very big topic. First, I had to talk about discontinuity, actually. So you would have to talk about how does the limit exist here, and the answer is yes. Um, hmm. I have to assume that you already know calculus for me to say anything here, don't I? So, huh. So, hmm. First thing I would say is slope is derivatives, right? A change of rate is a derivative, and the slope is a derivative. And how would I describe calculus in the most simplest manner? Well, I would call it the limits and getting to an infinitesimal point. So it's a forever point. That's the whole point of calculus. But how would you describe that actually? So if I were to get a fluid graph, any graph, it doesn't have to be time, but usually it's time with some y variable. So y equal t plus a bunch of t variables. Um, and then we would look at a certain point, try to get a tangent object. You don't know how to get a tangent object, but you're trying to get tangent at this point over here. At that one point, what is the tangent area over here? So at that one instance over here, and that's the idea of a calculus, right? What's the change of that? And so in reality, a derivative is measuring change in a sense. But is that the right way to describe it? Yes, it's measuring its change in that instance. Um, and it's idea of getting the tangent line. But in reality, how would you describe it even more simply? Because you also need to describe the area under the curve for integral. And usually it's Riemann sum that we do, which is not always true, but we get a small rectangle. That's one type of integral, actually. That's not all types of integrals. Statistics have a special type of integral, and there is substitution integrals, and there is many different rules for integrals, and that's not really how you would describe it, is it? Well, it's 22 minutes, so I'm going to stop. But it's an interesting topic I thought about. How would you describe this art? I mean, I could change your race, but in reality, you just have to keep on doing questions and until you understand it, don't you? But does question make you understand it, or does real science make you understand it? It's a very interesting observation because how I understood it was basically I didn't understand it until very later in life. I think high school I never understood. I mean, I understood it in the calculus term. I never understood the physics term until I went to college, and which is what I'm doing right now. And I now understand it because it's so simple now. But why did they never get it in high school? It's a question. Partly the blame is we didn't learn calculus fast enough. Well,